The harsh reality of zero gravity. Why artificial gravity is crucial. The problem. While exhilarating, prolonged exposure to microgravity, zero-G, has severe detrimental effects on the human body. Physiological impacts. Bone demineralization. Astronauts lose bone density at an alarming rate, similar to severe osteoporosis, making bones brittle and prone to fractures. Muscle atrophy. Muscles, especially in the legs and back, waste away due to lack of use against gravity, leading to significant weakness. Fluid shift. Body fluids shift upwards towards the head, causing puffy faces, bird legs, headaches, and increased intracranial pressure. Vision impairment, VIP. Swelling of the optic nerve and changes in eye shape due to fluid shifts can lead to blurred vision and permanent changes in eyesight for some astronauts. Cardiovascular deconditioning. The heart works less in zero-G, leading to a weakened cardiovascular system upon return to Earth. Disorientation and space adaptation syndrome, SAS. Initial exposure can cause nausea, vomiting, vertigo, and spatial disorientation. Long-term implications. For missions beyond the Moon, e.g. Mars, asteroid mining, and future space colonization, zero-G poses an insurmountable obstacle to human health and sustained presence. It's not just an inconvenience, it's a showstopper. The science behind fake gravity, centripetal force. The fundamental principle. The most scientifically viable and practical method for creating artificial gravity is through rotation, utilizing the principle of centripetal force. How it works, simplified. Rotation. Imagine a large space structure, like a ring or cylinder, spinning around a central axis. Inertia. As the structure rotates, everything inside it, astronauts' objects, wants to continue moving in a straight line due to inertia. Pushing outwards. However, the walls of the rotating structure continuously push inward, forcing the occupants to move in a circle. This continuous inward push is the centripetal force. The feel. From the perspective of someone inside, this continuous push against the outer wall feels identical to the sensation of gravity pulling them towards the ground. It's not gravity created by mass, but rather an inertial force mimicking its effects. Key factors. Radius, R. A larger radius is crucial. The larger the diameter of the rotating structure, the slower it needs to spin to generate comfortable artificial gravity. Rotation rate, omega, measured in revolutions per minute, RPM. Slower rotation rates are preferred to minimize negative side effects. Formula. The artificial gravity experienced, acceleration, A, is directly proportional to the square of the rotation rate and the radius, atro omega 2r. Why a large radius? A large radius allows for a slow rotation rate, e.g. 2 to 4 RPM for 1G, which minimizes the uncomfortable Coriolis effect and makes the artificial gravity feel more natural. From sci-fi visions to engineering challenges. Sci-fi grandeur. Movies and TV often depict vast, rapidly spinning space stations, e.g. 2001, A Space Odyssey, Elysium, that effortlessly provide artificial gravity. Real-world hurdles. Translating these visions into reality presents enormous engineering, logistical, and scientific challenges. Massive scale. To generate comfortable 1G artificial gravity with minimal side effects, like the Coriolis effect, structures would need to be hundreds of meters or even kilometers in diameter. Building such immense structures in space is a monumental undertaking. Construction and assembly. Launching the necessary materials and assembling these colossal rotating habitats in orbit would require unprecedented resources, advanced robotics, and new construction techniques. Structural integrity. A large, spinning structure must withstand immense internal stresses from rotation, as well as external forces like micrometeoroid impacts and orbital debris. Coriolis effect. What it is. A perceived sideways force felt by objects and people, Moving in a rotating reference frame. Impact. In smaller or faster spinning habitats, moving your limbs or walking can cause disorientation, nausea, and difficulty with fine motor control due to this effect. This is why a large radius, and thus slower rotation, is vital. Energy. Requirements. Spinning up and continuously maintaining the rotation of a massive structure requires substantial energy, which must be generated in space, e.g., solar arrays, nuclear power. Leakage and pressure. Maintaining a breathable atmosphere within such a large, complex, and potentially modular rotating structure is a significant challenge for sealing and pressure management. Other gravity concepts. Brief dismissal. Constant thrust. While continuous acceleration provides artificial gravity, it's incredibly fuel-intensive and unsustainable for long durations. Exotic physics. Concepts like gravity generators or manipulating gravitons are purely speculative, with no current scientific basis or observable phenomena. The imperative for the future of space travel. Beyond exploration, sustained presence. Artificial gravity isn't just about comfort. It's about making long-duration human presence in space truly viable and sustainable. Key benefits and necessity. Health and well-being. Eliminates the debilitating health effects of zero-G, ensuring astronauts remain healthy and capable for extended missions and upon return to Earth. Comfort and psychology. Provides a sense of up and down, making space habitats feel more like home and reducing psychological stress and disorientation. Simplified operations. Tools won't float away, liquids will behave normally, and everyday tasks become far easier. Growing food, exercising, and maintaining equipment all become more efficient. Enabling long missions makes multi-year voyages to Mars, the asteroid belt, and beyond feasible for human crews. Space colonization. Essential for establishing permanent human settlements and viable ecosystems in space, allowing for the growth of future generations without gravity-related health issues. Space tourism makes space travel accessible and comfortable for a broader range of individuals, potentially opening up a new industry. Glimpses of the future. What's next? Current research. Scientists and engineers are actively exploring various approaches to artificial gravity. Concepts under development. Centrifuge modules. Smaller human-sized centrifuges within existing space stations like the ISS to provide intermittent artificial gravity exposure for astronauts, mitigating some zero-G effects. Tethered systems. 2 spacecraft or modules connected by a long tether, spinning around their common center of mass to generate artificial gravity. This could be a stepping stone to larger structures. Modular assembly, designing future space stations in sections that can be assembled into large rotating rings or cylinders over time. Variable gravity facilities, research on how much gravity is enough, e.g. lunar or Martian gravity levels, to sustain human health, which could reduce the size and rotation requirements. The path forward. While a Starship-scale spinning habitat might still be decades away, the scientific understanding is solid, and ongoing research is chipping away at the engineering challenges. The future of humanity in space hinges on overcoming this missing link.